now that we've talked about the elements of a hypothesis test, and we talked about the steps on the five-step method for doing a hypothesis test, we're going to go through examples and actually how to do these things, okay? Now, in 9.2, we're going to be doing a z-test for the population mean, okay? Just like in chapter 8, when we got to 8.2, we did a confidence interval for the population mean. Now, this is very important. In these examples, the standard deviation is known. Since we're doing something about the population mean, and the population standard deviation is known, we'll be using the z-test. That means we're using the z distribution. Okay? So if you're looking at my notes, I have the five-step method on there. Okay? Let's read through the five-step method real quick. It says, set up the null hypothesis and the alternative hypothesis. So that's going to be the first thing that we do. And I do have an example below. So H naught is going to be something. HA is going to be something. The second step is select the correct test and identify the significance level alpha. So the second step, alpha is going to be equal to something. And not only that, selecting the test is either going to be a left tail test, a right tail test, or a two-tail test, okay? But we can't select that right now. We need to come up with our alternative hypothesis first, okay? And then we're going to calculate the p-value, all right? From the p-value, we're going to use it to make a decision about whether we reject the null hypothesis or do not reject the null hypothesis. Okay, so this is the p-value method. We're calculating the probability. So p-value is the probability that we obtain the sample mean. Okay, this relates back to chapter 7 when we talked about the central limit theorem. So what we're going to do is we have a claim about the population parameter, and to test that claim, we go collect sample data. From that sample data, since we're talking about the sample mean, the population mean, we need to find the sample mean. And then we calculate the probability that we obtain this sample mean. If you recall, that's what we were doing in chapter 7, the central limit theorem. Okay? You use the central limit theorem when you are being asked about the probability of the sample means, okay? If you were to keep collecting samples over and over and over and over, all the same size, you were to find all of their sample means. The distribution of the sample means form a normal distribution. That was the point of chapter 7, okay? So, the p-value is just the probability that we do obtain that sample mean. Now, based on that probability, if p-value is less than our alpha, oops, that's an infinity symbol, is less than our alpha value, reject our null hypothesis, okay? It's a very clear definition. You find your p-value, and if it's less than your alpha value, you reject your null hypothesis, okay? Now, if p-value is greater than or equal to alpha, well, if p-value is less than alpha, as you reject, if the p-value is greater than or equal to alpha, do not reject the null hypothesis. Okay? Rarely is it ever equal to. It's usually either greater than or just less than. Okay? But now let's go ahead and look at our first example. I really like this example because it can explain a lot of things, especially some previous material. Let's see. It says a baker claims that his bread is more than 15 centimeters. Okay, the height of his bread is more than 15 centimeters. So if I just have, you don't have to draw this. There's my loaf of bread. Okay. So he's not talking about like how long it is or the length of it this way. We're talking about the height of it. Okay. He says his claim is that his bread height is more than 15 inches on average. So this height here on the average is more than 15 centimeters. Okay, let's see, I could draw that a little better. Mu is more than 15. Okay, so that's his claim. Now, we got to look at this, and we got to decide where to put it. Are we going to put it in the null hypothesis, or are we going to put it in the alternative hypothesis? Now, again, you got to be very careful with this wording. He says the average is more than 15. Just more than, there is no equal to sign. If he would have said instead at least 15, there you would put an equal to sign. But he just says more than, so we got to be more than. This is strictly more than 15. Now, since it does not have the equal to sign, the alternative hypothesis always had the one that didn't have the equal to sign. So that's where that's going to go. That's going to go in the alternative hypothesis right here. Mu is more than 15. And this is our claim. That's what he's claiming. So from here, I mean, we haven't even finished reading the problem. This is just the very first part, setting up our null and alternative hypothesis. We can get our null hypothesis right now. So, remember, these are both contradictory. So, mu is still going to be here, 15 is still going to be there. But what is the exact opposite of greater than? Less than or equal to. The null hypothesis always has an equal to sign on there. And if this is greater than, the opposite of greater than must be less than. Alright, so we got our null alternative hypothesis set up just from the first sentence. Okay? So let's keep reading. Let's read it again. A baker claims that his bread height is more than 15 centimeters on average. Several of his customers do not believe him. Okay. So that's fine if they don't believe him. But now, here's what he's going to do. To persuade his customers that he is right, the baker decides to do a hypothesis test. Okay? The baker knows from baking hundreds of loaves of bread that the standard deviation for the heights... So this is what they're telling us. He bakes a ton of bread all the time. So he knows what the standard deviation is for all of his bread. He's telling you a population standard deviation here is 1.5 centimeters. And this is going to be the central key here to tell you what type of test you are doing. They're telling you the population standard deviation. We're talking about a mean. We should use the z-test. In the next section, we won't know the population standard deviation. We will be given the sample standard deviation. And since we're going to be talking about means, we don't know the population standard deviation, but we know the sample standard deviation. We will be using the t-test. Okay? So you really have to pay attention to whether you know the population standard deviation or not. Okay? So let's see. And the dimension or the distribution of the heights is normal, okay? He bakes 30 loaves of bread, so they tell us the sample size, n is equal to 30. and finds that the mean height of this sample, so the average height of this sample, is 17 centimeters. Okay? Using a 0.05 significance level, that's your alpha, so 0.05. Does the sample data provide evidence that the mean bread height is more than 15 centimeters? They're asking us, does our sample data provide evidence that my mean bread height is more than 15 centimeters? Do I have enough evidence to say that my claim is correct? Because this is my claim. Okay? So, now we're going to get the p-value, because that's the next step. We already went through setting up the hypotheses. We got the alpha value that was told to us in the problem. Oh, I guess we have to say whether it's a right-tailed, two-tailed, or left-tailed test. And if you remember how to get that, you look at the alternative hypothesis, and you see how the inequality sign is pointing that way. Like if you were to draw an arrow, it's pointing that way. So this is a right-tailed test. All a right-tailed test means, if we have the normal distribution like that, and we're calculating areas, we're calculating the area to the right that way, okay? A left-tailed test would be, we're calculating the area to the left. A two-tailed test would be, we're calculating both tails of our normal distribution, okay? So that's all that's doing. When we find the p-value, remember, probability is the area under the curve. When we find the p-value in this case, we are finding the probability in this right tail. That's what we're doing since it's a right tail test. If it was a two-tail test, we'd be finding the probability in both tails. Left tail test, probability over in the left tail. Okay? Alright, so let's go ahead and calculate our p-value. We don't need any of this right now. Let's go ahead and erase it. And when we do a hypothesis test, we assume the null hypothesis, which was mu is less than or equal to 15, assume the null hypothesis is true, okay? That's how you always start these. Now, the p-value. If you want the p-value, this is a, remember we're doing a right-tailed test over here. We need the probability to the right. We know how to find the probability of the right of normal curves. That's normal CDF. Well, we need our lower bound. Our lower bound is 17 because we want 17 and bigger. Okay, it's a right-tailed test. The mean here is 15. That's our population mean. So we're assuming that mu is equal to 15 here. So our lower bound, 17. Our upper bound, just some really big number. I use 100. The mean, 15. And then the standard deviation. We are using the central limit theorem here. And if you recall, the standard deviation, you just don't put the standard deviation there. You have to divide the standard deviation by the square root of your sample size. These are exactly how we did problems in Chapter 7. Okay? So, let's see. Grab the calculator. Second vars, there we go. I was thinking of the second stat. Second vars, you go to normal CDF. The lower bound is 17, the upper bound is 100, the mean is 15, and then the standard deviation, 1.5 divided by the square root of 30. Okay? I have the nice menu. And as you can see, when I entered the standard deviation, I just typed it in exactly how I wrote it over there, 1.5 divided by the square root of 30. It's going to calculate that number for me when I go to paste. Okay. Now, if you have it where it doesn't give you that menu and you got to write it in a line, you just write it in a line just like how I have it written on the board right here. And then you go ahead and hit enter. So, we get the p-value is equal to 1.41. You see an E here, negative 13. This is scientific notation. What this really means is 1.41 times 10 to the negative 13 power. Or in other words, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 141. Okay. So, this right here, this is our p-value. It's really tiny, okay? Now, let's talk about what this p-value means for a second. If the true population average height of these breads is 15, and if we were to collect a sample of 30, the probability that that sample has a sample mean of 17 is this really tiny number right here, okay? That means if we were to collect a sample, we should not have gotten a sample mean of 17, okay? That's a really low probability getting this, and that's assuming our null hypothesis was true. Look at our null hypothesis. Mu is less than or equal to 15. So we're going to say it's equal to 15, which is the highest it can go. Under that assumption, we got a sample mean of 17. But based on the numbers, it is very unlikely that I should have gotten a sample mean of 17, meaning my original assumption that this thing was true, that it should be 15 or less, must be false. Okay? It must be false. Now, we do have that criteria that says if this is my p-value, if it's less than alpha, this number is definitely less than 0.05. Okay, this is a really, really tiny number. Since the p-value is less than alpha, we're going to reject our null hypothesis. We reject that the mean is less than or equal to 15, okay? So that's what we're actually doing. We're finding the probability that we get this sample mean and comparing it to our level of significance. Now, let's go ahead and write up our results that we have here. Okay, I'm going to keep my p-value. I'm going to write up my null and alternative hypothesis and everything. And let's write our conclusion. So we have our null hypothesis, which was mu is less than or equal to 15. We have our alternative hypothesis, which says that mu is greater than 15. And remember, this was our claim. Okay? That was our claim. That's going to be very important where our claim is. And then we had an alpha value of 0.05. This was a right tail test. And then we found our p-value to be 1.41 times 10 to the negative 13. Based on these two, we compare them, and our decision is to reject our null hypothesis. Okay? That's what we've decided right now. Okay, so let's talk about our conclusion here. Our conclusion here, what we can say is, let's see. I'm trying to think of how I should write this. So, there is, now here's our claim, right? Here's our claim. We rejected the null hypothesis, okay? We reject this one, meaning since we rejected this one, don't we have evidence that supports our claim here? Now, if we do not reject this, we wouldn't have enough evidence to support our claim. But we did reject this, so there is enough evidence to support the claim that, there's enough evidence. I forgot a little phrase in here. We could stick it at the end. There's enough evidence at the alpha is 0.05, at the level of significance of 0.05. You need that statement in there to support the claim that the average bread height is more than 15 centimeters. So you kind of just rewrite what the claim was. Now, this is going to be very important whether there is enough evidence or there is not enough evidence for your claim. There's many ways of writing your conclusion. One consistent way that I like of writing the conclusion is to make a conclusion about your claim, okay? Your claim was here. Since we reject this, we have enough evidence for this. So there's enough evidence to support our claim. Now, if our claim was up here, okay, and we rejected this, we would say there's not enough evidence to support our claim, okay? So it really matters where the claim goes. Now, there is enough evidence to, at alpha is equal to 0.05. I forgot that piece right there, okay? Now, let's talk about our p-value one more time. And let's talk about it in relation to our alpha value. Remember in the introduction videos, I said the alpha value is the largest maximum allowable error or maximum allowed probability for a type 1 error, okay? When we find this p-value, although it came out to a conclusion of rejecting the null hypothesis, we could do this study one more time and we could get a different p-value. What if we get a p-value of 10? Like 10%, 0.1. Then 0.1 is definitely greater than 0.05, then we would not reject this, okay? We could have made a type 1 error when, remember, our sample mean came out to be 17 centimeters. That's really high for our average because he said it's more than 15. Now, this could be a type 1 error. Type 1 errors can happen as a result of bias, or they can happen as a result of chance or something. Let's talk about the bias for a second. Knowing that his customers are claiming this, that his bread, they don't believe him, when he makes these 30 loaves of bread, what if he purposely puts extra dough in there so for sure they come out bigger? That would definitely skew his results, and right there, that would cause us to get a small p-value, okay? Now, if he were to do everything correctly, everything right, and not put any bias in there, make the bread exactly the same way that he did, and then he still gets the sample mean of 17. Oh, this should be X bar. And we still get a p-value, then instead of saying that we made a type 1 error, then we probably did get something out of the normal, making our data significant to reject the null hypothesis. Okay? That's why, like in pharmaceutical companies, when they do hypothesis testing, they want to be sure that they don't have type 1 errors. That's why their level of significance is a lot smaller. Okay.